this very precious opportunity to talk about my work. And at the workshop, I will talk about, of course, dynamo problem related to cross-helicity. But here, today, I will talk about helicity effect in hydrodynamic turbines. And yeah, I kept a very good connection with Bob Krashner, as Igor mentioned. But as far as my work is concerned, he said to me, you are crazy to treat such a very complicated problem using closure theory. Anyway, so I could not publish any paper with him because our approach is, in this sense, very different. Anyway, okay. So this is outline of my talk. Oh, so first of all, my English is still very bad. So sometimes I start with an inappropriate verb. So in such a case, my talk becomes very turbulent state. So please be patient with my this state. So this is outline of my talk, and first I introduce something about helicity, and I'll present some theoretical analysis of Reynolds stress, and these things are application of the result of this analytical result, and swirling flow, vortex dynamo, and helicity subgrid scale modeling. So, helicity, in my talk, throughout my talk today, I confine myself into the incompressible case. Of course, I know the importance of compressibility, but in this talk, this is the total amount of helicity. Omega is vorticity, and this is turbulent helicity density. Sometimes I call it helicity, just helicity. And this is mean field helicity. So, okay. So, as all of you know, so helicity has several important properties. One is the implicit invariant of 3D Navier-Stokes equation, as well as like the total energy. And also, helicity is related to topological or structural information of turbulence. And helicity can be interpreted as a notedness of vortex tubes, as you know. And also, very important property is helicity is pseudo-scalar, unlike energy. So it's not positively definite, and it changes its sign under the inversion transformations. You know, and because of these properties, in mirror symmetric system, statistically cross helicity pseudo-scalar is 0. So in the sense, presence of finite helicity means some breakage of mirror symmetry. So it's a very good quantity to express the breakage of mirror symmetry. So this is often so we can see, for example, Keith Moffat's books. Then helicity can be interpreted as a notedness of two vortex tubes. And my point here is that because of this, if helicity conserved, because of this conservation of degree of notedness, so vortex tubes cannot evolve freely. So there is some constraint on dissipation. So in this sense. And also in a very naive sense, so if we consider the vortex equation, vortex induction equation, And if we have vanishing of U cross omega term, then we only have diffusion due to molecular diffusivity, molecular viscosity. So this suggests that, as we see from the sine and cosine relation, so if we have a finite amount of helicity, it may express the weakness of nonlinear mixing in this sense. This is very naive argument, but so we can easily consider helicity may be related to suppression of nonlinear energy transfer or nonlinear mixing. Okay. So my talk is not so comprehensive. So, but I just talk about several works, and so sorry, I didn't write the Nathan and Igor's work, and also works related to here, people here. Anyway, because of such nature of helicity, helicity can be argued, has been argued in the context of inverse energy cascade or negative viscosity in helical turbulence. So these are pioneering works. And also, but because of the symmetry of Reynolds stress, so helicity itself is not sufficient to work for vortex generation, large-scale vortex generation. So further breakage of symmetry is required. So someone considers compressibility and also anisotropy. Uriel considers anisotropic effect, and also Gubarmadze and Komenko and Ta considers the presence of non-vanishing mean helicity is important. So, so my work is in this sense very similar to this approach, in some sense. Okay, so this is some fluid turbulence researcher considers inhibition of energy transfer will be occurred in the presence of helicity. So this is a very famous work by André and Lechoux. And so this is a temporal evolution, and this is energy and cross helicity. So without helicity, energy decays something like this. But with helicity, it is shown by numerical simulation. Energy cascade is suppressed to some extent. But in the calculation, inhibition of energy transfer occurs in early stages. Yeah, but with the decay of helicity itself, such effect disappears. That's one point. This is a homogeneous isotropic calculation. And also work by Perez and Victor and also something like this. So they make some conditional sampling of this is the sign of the velocity of u and omega, and this is a very high dissipation range of channel and also Taylor-Green vortex, and this shows a very small dissipation range, dissipation region of channel and vortex. Then it shows that, so they show it that, so high helicity means cosine theta equal 1 or minus 1. So so this shows that in the region where the dissipation is very weak, the helicity is very strong, plus and minus helicity. But and also in the Taylor vortex they shows. But rightly after their simulation, Rogers and Purvis-Moen showed using a direct numerical simulation that their Peltz-Edwards result is not correct. So due to the lack of resolution and also lack of sufficient ensemble average. Anyway, so they show that this is the isotropic turbulence case. Initial state is homogeneously distributed. This is histogram of alignment. Okay, so in the developed state, they have in 4 region of the flow. So they conditionally pick up probability distribution of the low dissipation region and high dissipation region, but they couldn't see any significant difference between these two.
Are you talking about eigenvectors of the Sij matrix? Or what alignment are you talking about?
This is the U and omega, alignment of U and omega. So velocity and
that's also what you showed in the previous plot, right?
Yeah, yes.
Is it true that in reality maybe not suppressed?
Yes, in their simulation condition, helicity effect is not tenuous. Yeah.
But in the previous plot, you had a much stronger.
Yeah.
Peak. What is the difference?
So the difference, they argued the difference of the result, discrepancy of the result, and they concluded that the previous calculation has not enough resolution, and also the sampling is not enough, and also the previous result is not reached to some steady state. Still.
And helicity is introduced in these simulations by forcing. What is the reason for kinetic helicity here in these simulations?
Yes, in this case, that's another difference. Previous work, they impose some finite helicity in condition. Then she decay.
By forcing or what?
By forcing, I think. So I think forcing. Yeah. And so this is isotropic turbulence and also channels. And this is joint probability and function. And you see, this is the dissipation rate. This is cosines. So if this is the channel, so all quantity is different depending on the distance from the wall. So this shows several difference. Anyway, so the conclusion is that they could not see any substantial difference between in the low dissipation region and high dissipation region. And low dissipation region is only 1% of the flow. And this is high dissipation region is only 1%. And all these profiles is the same to the 100% profiles also. So they concluded that relationship between helicity and dissipation is tenuous. Okay, but still, but still, as some work shows, so the large-scale vertical generation is a reality of life, and some people consider the helicity may work for that. So now, then I made analysis of the helicity effect. So I often show this cartoon to show how many approaches to turbulence exist. So anyway, so I hope.
I think it's picture of science in general.
Okay. So I hope I grasp some essential part of turbulence, but important thing is to communicate with the other researchers. Anyway, so so there are several approaches, and I will show my standpoint. So this is the fluctuating velocity equation, and we already divided the field quantity into averaged one and fluctuating one. Averaged one as capital and fluctuating part is prime quantity. So fluctuating velocity contains this type of term, coupling of fluctuation and mean velocity C. And also fluctuation, coupling of fluctuation and fluctuation. And if I roughly divide the approaches, one is the instability approaches. So they neglect this turbulence interaction. Then consider the effect of large-scale inhomogeneity. So this is, as you know, this is a linear in U prime and P prime. So we can solve this type of equation in some method. And
this is valid for small Reynolds number,
yes.
Okay.
Yeah. And closure approach. Most of fluid researcher work is this type of one. They neglect this type of inhomogeneity at all. Then concentrate it on the analysis of this effect. So this is a homogeneous turbulence, no dependence on large-scale inhomogeneity. So closure problem is something like this, but I will skip this one. And so this is closure theory for inhomogeneous and anisotropic turbulence is starting. My standpoint is something like this, starting from nonlinearity. So closure theory for homogeneous turbulence, then towards approaching to realistic turbulence. And another approach is starting from inhomogeneity to instability. In turbulence theory, this type of approach is called rapid distortion theory. So then self-consistent instability
But
theory.
rapid distortion theory is valid only for very strong shear.
Of course. So for them, nonlinearity is not so important. Of course important, but the secondary. So very strong shear is essential. So it of course depends on the time scale of shear and also eddy time scale. So my approach is something like this. Anyway. So this is my approach, but so you may not interested in this type of. We use the closure theory for homogeneous turbulence. Like DIA, direct interaction approximation by Bob Krashman, and it's first order line renormalization. And with the aid of multiple scale analysis, then we combine these two methods. So this is introduction to scales and the velocity fluctuation equation. This is then large scale inhomogeneity effect is perturbationally included like this. Okay, this is the same equation for the homogeneous isotropic, but as perturbationally we have effect of large scale inhomogeneity. Then we can write down the first order field equation, something like this. Then the left hand side is the same, similar to the homogeneous isotropic equation, but we have right hand side which depends on large scale inhomogeneity.
So one small parameter is here is ratio of integral scale to shear scale, large scale shear
Yes,
scale.
sir,
And what is the other small parameter in the system? Small interaction.
Yes, so because we use DIA, so in this sense, for the basic field, I may say background field,
Yeah.
we consider, for example, some Gaussianity is other first approximation good one. Also, we introduced green function for this nonlinear equation, but green function is only for linear equation, as you know. So in this sense, this is also the small parameters. So this is green function response to the very infinitesimal forcing or some disturbances. So green function is something like this.
And the ground turbulence is a given, yeah? So you
No,
impose perturbations to the background
given.
turbulence and study deviations from the background turbulence, and this deviation is small. So this is a main assumption of the system.
Main
yeah?
assumption,
Okay.
starting point.
So
Yeah.
this is perturbation approach.
Yeah, perturbation. But still, yeah. As any other perturbational approach is what I said, we use renormalization. Renormalization. So that means we assume, as I show it here, we assume for basic field, background field is homogeneous, or sometimes usually isotropic. But finally we renormalize. So we consider the green function for the real field.
So this is like a usual, in a usual renormalization group approach, yeah?
Yes, in this sense. But yes. Yes. Summation is partially, but infinite number of terms is included, but in terms of field theory. Yeah. Okay. So I calculated Reynolds stress using such a method. So this is the basic field. So ground state of turbulence, and also background state, and also perturbative field related to inhomogeneity of large scale field. Then we can calculate Reynolds stress, something like this. So Reynolds stress is written in this case. Of course, we have several other terms, but as a first expression, we can get eddy viscosity representation of Reynolds stress. Okay, and but eddy viscosity is expressed using the green function and energy spectrum in wave number space. So if you see, the green function gives a weight for time. So this gives time scale.
So you reproduce actually the results of Orszag-Yokoi. Just this green equation.
Yeah.
This is the Orszag-Yokoi 1985 result. I think.
It's no result, it's coefficient for no.
The same coefficient.
You mean your result?
No. Orszag-Yokoi.
Yeah. Good. Yes.
Okay.
So this is one loop calculation.
What?
So this is one loop calculation, is it?
Yes.
This is what is called
Line
one loop.
normalization of the first order. Yeah.
Yeah.
Not Bartik spat. Only propagator renormalization. Because we use DIA. Anyway, the point is that so this part is not how to say essential for my talk today. So this is I just show this one because I'd like to show the approach of mine. So anyway, eddy viscosity is expressed using energy. Energy spectrum integrated by wave number and also time scale. So it gives tau k or tau uu. So the simplest expression of eddy viscosity is this type of mixing length. So this is a generalization. The form of itself is 1970, not inhomogeneous turbulence, but already Bob Krishna showed 1970s or something. This expression itself.
It's still incompressible, yeah?
This is incompressible, but of course it can be straightforwardly to compressible case. And also, now I almost finished my work on. So in this work, I start with homogeneous isotropic basic field. But homogeneous is important because we consider the wave number space. But isotropy is not indispensable. So we can consider analysis. Anyway, so in this approach, so inhomogeneity can be treated as a higher order term. And order one, eddy viscosity term coming this first order. And also helicity effect coming to the higher order. Okay. So anyway, so I skip. So this is the fundamental equation I considered. This is the Navier-Stokes equation in rotating plane in incompressible space. And this is the Reynolds stress. Okay. Then we assume as a basic field this is a general form of homogeneous isotropic velocity variance in wave number space. And this gives energy spectrum, and this gives the helicity. So this second term gives allows us to study the non-mirror symmetric case. In mirror symmetric case, we only have the first term. So due to this term, we can incorporate the effect of helicity using this approach. Okay. So this is the result. So this is the Reynolds stress expression. So from the lower order term, we have eddy viscosity representation. But from higher order term, we have this type of contribution to Reynolds stress. This is frame rotation. Omega F is small frame rotation. And capital omega means vorticity in my work. So gamma is expressed using the Green function coupled with gradient of helicity spectra in wave number space. Anyway, so we have nu-t expression. So eddy viscosity is expressed using turbulent energy because it's expressed spectrum of energy. But this term, this gamma is related to the gradient of turbulent helicity, as you see. And coupled with large-scale vorticity or rotation, we have this type of contribution, which may balance to this eddy viscosity effect.
Remind me again of G. What is G?
Sorry?
G.
G gamma? G, no?
No, G. In the
G is Green function. Green function for the governing equation.
Could you please remember omega F, what is it omega F?
Omega is frame rotation.
And omega capital?
Capital is large-scale vorticity.
So you introduce here only inhomogeneity of kinetic velocity, not inhomogeneity of turbulence, yeah?
Yeah.
Because
Yeah.
gamma is proportional to gradient of kinetic velocity.
Yeah. And
Light is not inside your background turbulence. So if you introduce inhomogeneity,
No, but that's uniform. Background turbulence.
no,
will be
background turbulence is uniform. How you can obtain homogeneity of kinetic velocity?
Right here.
no, kinetic energy is not homogeneous.
What is the gradient of HB?
What is the gradient of HB?
Yeah. What is the HB?
HB is, oh, I see, yeah. HB is this quantity.
So this implies that this is the gradient of small scale kinetic velocity.
Yeah, just think of going through the equator. You have turbulence, you're going through the equator. At the equator it's 0, and north and south it's opposite sign.
Yeah, I understand, but it should be introduced by background turbulence.
Otherwise
Otherwise,
uniform. But that's uniform.
so this implies that you have generation of kinetic velocity in the system, which is inhomogeneous.
No,
No, it's-
so what you meant to say is that this only shows how to say breakage of mirror symmetry. So if this quantity is zero, we have no.
Not zero, but question is about the gradient of this quantity.
the gradient of kinetic velocity, which is non-trivial. So you need to have some dynamical equation for evolution of kinetic velocity,
Of course, we consider.
which is for non. This is
Because we
equation
consider
should be for-
inhomogeneity. By inhomogeneity, I mean shear turbulence. Because we have velocity shear, velocity gradient, which gives us coupled with some factor, helicity and its inhomogeneity. Okay, so later. Okay, but this is integral expression for these transport coefficients. It's very heavy for real application. So we will use some turbulence modeling using 1-point quantities like turbulent energy and its dissipation rate and turbulent helicity. This is the 1-point quantity defined in configuration space, not the wave number space previously I showed. Then express using the system of equation K, epsilon, and H, or sometimes dissipation rate of helicity. I will make some self-consistent system of equation. So in this approach, so all turbulence field is expressed using, for example, turbulent energy, 1-point energy, dissipation, and helicity. And this is turbulence. And we also consider some mean field. Okay, then radial stress can be modeled as this. So this is usual eddy viscosity representation. Then this is vorticity related part, and this is the 1-point helicity gradient. Okay. So we see the gradient of turbulent helicity coupled with mean vorticity with also the system rotation may contribute, it will contribute to this stuff. Contribute to the Reynolds stress. Okay? So we can model the, in a simplest case, we can model nu-T, eddy viscosity, turbulent energy multiplied by time scales of turbulence. And also gamma, and gamma is written using something like this.
And you have here imposed shear to the system or not? Or shear is generated with the generation of homogeneity of electricity?
Not imposed.
You don't have here impulse shear.
You can do it.
Because we consider the mean velocity equation.
Yeah, I understand. Yeah.
So through the transport coefficient and some other inhomogeneity effects, U itself is solved self-consistent, not important.
But important is, for example, you want two plates which go in the opposite direction. Two plates.
So this is very general expression. So we can consider. And this is the equation for turbulent energy and turbulent helicity. So this is turbulent energy production, dissipation, definition of energy production. So we, as you know, we have shear of large scale coupled with fluctuation. Then we have turbulent energy production. Also, the same things can be said to helicity production, turbulent helicity production. So if we have inhomogeneity of omega, inhomogeneity of vorticity coupled with Reynolds stress and this type of coupling, then we have the helicity production for turbulent helicity production. Also, very important term is related to this one. If we have energy inhomogeneity, this is divergent form. So if we have energy inhomogeneity along the vorticity or rotation axis, then we have a mechanism which gives which makes some distribution of helicity. As I mentioned, helicity is not positive definite. So even if the total helicity equals 0, it can be distributed in positive and negative depending on the situation. So this gives such. And I think this is in practical application of helicity equation, this term is very important. Because this is directly related to system rotation. So if we have very small, even small energy gradient along large scale rotation, we have a very strong mechanism to give the plus and minus helicity in the upper and lower hemisphere.
G, capital G, this is...
yeah, G, sorry, G is not green function here. G is energy or helicity for one point quantities. Okay, so, and also we need the equation for dissipation. So I know this is very problematic, but in engineering field, this is already to some extent established. So this is, I also almost published my paper on how to derive dissipation equation. But anyway, so this is a very established form of engineering field. Anyway, so and we have Reynolds stress expression as I showed previously, like this. And the transport coefficient is expressed K and expressed in terms of K, energy and dissipation rate epsilon and helicity H. So mu T is expressed time scale multiplied by K. And eta, helicity related term is expressed like this.
No,
Yes.
I just would like to understand physics
Yeah.
here. So you started with homogeneous turbulence but helical.
Yes,
Then,
but only basic field.
Yeah, I understand.
Yeah.
Then you have here generation of differential rotation, yeah? Because omega, okay, alpha is
Capital omega.
vorticity, yeah.
Yeah,
You have
vorticity.
generation of vorticity here, and vorticity can produce gradient of kinetic helicity.
Yeah.
Background kinetic helicity.
Yeah. Background, yeah, also.
So, you force is proportional to vorticity controlled by second derivative of helical particles. Very interesting.
Yes, it's in nature, I think it's self-consistently determined. Yeah.
Enough to say that it's possible.
Impossible?
Enough to say it is possible.
Possible. Yeah. Okay. So let me start with swirling flow. So swirling flow, this is very famous laminar pipe flow. So my point is that turbulent energy gives intensity information of turbulence. And we need some other information which represent structural information of turbulence. One possibility is helicity in this case. Okay, so this is laminar flow, and I might have already showed this most of you. And in turbulent state, we have mean field is something like this. So it's very flattened. So, but if we add rotation, so primary effect of turbulence is like this. So due to this is Reynolds stress expression. So if we substitute this into Reynolds stress, then we have this type of enhancement of molecular viscosity. So effective viscosity is enhanced. We have enhanced transport. And also, nu-T is not a property of fluid, but flow. So nu-T itself, spatially and temporally, has dependence. So then we have this type of very flat profile in main part. If we only multiply the molecular viscosity, we still have parabolic profile. So this type of spatial dependence is very important. We have this type of. This is coming from this turbulent viscosity. But if we add rotation, we again have this type of profile. This is the turbulent swirling pipe flow. So if we add swirling inlet region, then we have a dent in the central region of the flow. Then it decays, then recovers this type of turbulent profile.
Which type of boundary conditions we have for the...
It's very good question. So to exactly speaking, the profile change depends on where we impose, for example, angular velocity, angular momentum. So if we impose in the center region of the pipe, we have this type of dent or deceleration in the central region. But we add angular momentum in the outer region. Then we have opposite. That's very interesting point. And this is related to the axially rotating pipe flow. In axially rotating pipe flow is flow itself is not imposed to rotate, but outside of pipe is rotating. In this sense, angular momentum is supplied in the outer region. In such a case, this type of parabolic-like structure again. So this is the actually experiment by Imao. So this is laminar, this is turbulence, and with rotation, n is rotation number. Then we someone says this is relaminarization, but this is a highly turbulent state. So from the viewpoint of turbulence modeling, these phenomena is very difficult to reproduce. So I will skip. In laminar case, we several arguments, including vortex breakdown or something, but I will skip this argument. Okay, so this is another experimental result by Steenbergen in Netherlands. and 1995, and this is circumferential velocity, so rotational velocity. So this is the pipe center, and it's very strong rotation, almost rigid rotation near the center, and vortex-free rotation part. This is something like Taylor vortex or Rankine vorticity. Then this is the axial velocity profile. So if we have this type of rotation, then we have a dent in the center region. But as the rotation profile changes, something like this, this is already rigid rotation here. Then this type of flat profile recovers.
So the swirl, or the swirl is put in by hand, is that right?
In this case, using some, how to say, bend.
Yes.
Then
okay.
so they use some
Yes.
pipe and hands. So
I see.
then,
Yes.
yeah,
So the geometry of the.
yeah. And this is very interesting problem. But anyway, I will approach this problem using the helicity incorporated to my model. And also, this type of swirling flow is very practically very important. Some of our launch failure of the rocket is related to this problem, because we impose gas to the turbine engine using some swirling. But due to the swirling motion itself, in some part, in central part, we have a reversed flow, and which propagates the cavity to the propeller itself. Then this type of damage will be anyway, so.
Is that known? Do they know that?
Some, if I'm not wrong, some engineer already noticed this problem, but due to some payload problem, if, as I can show you how to determine this condition, but if pipe radius is a little bit more big, this problem never occurs, I believe. And experimentalists know with such tendencies. But because of...
So your guess is that we are back to laminar flow?
No, not laminar flow. But this degree of inverse depend on, in my opinion, depend on the combination of flux we give and helicity we give. So
these profiles are still profiles of the mean flow.
So yes, this is mean flow. Mean flow. Still mean flow. So.
But I mean, your eddy tensor, Reynolds tensor, doesn't have any helical contributions.
This one doesn't give any,
Yeah,
as it is. But as I showed, there are some additional term related to helicity.
Did you try to plot the average mean kinetic energy over the flow?
Kinetic energy?
Yeah. U prime squared average.
Sorry, I didn't know that. So, but
I think that would be very interesting to understand the degree of turbulence. How it's different from the wall to the center of the flow.
Yeah. Experimentalists already, of course, observed each intensity of turbulence, each component of Reynolds stress in this sense. So if you are interested in, I can show you later. Anyway, so this type of AD viscosity is how to say not applicable. No power to explain and predict this tendency.
And isn't it already because it is an isotropic quantity? And this situation is not essentially not isotropic.
That's very important. But still, some people consider this is how to say eddy viscosity representation. But some engineering people consider the Reynolds stress modeling. That's they solve the equation for each 6 component of Reynolds stress. Even such modeling, this type of very difficult. In such a Reynolds stress approach, Reynolds stress modeling, we call it second order modeling. So we can treat the anisotropic effect, but still it's very difficult. And some engineering people found that if we change the coefficient model constant if they reduce it to 10% or sometimes 5% or something, then this type of profile can be recovered. But it's not physical, very ad hoc approach.
It's not 10%, it's from 9 down to 1.
Yeah. And someone said 1% is good for predicting this type of swelling. So actually, some engineering design phase, this type of model change is really good. And my point is that so we need to consider the helicity or breakage of symmetry, because if I add a rotational motion, it certainly gives the breakage of mirror symmetry. So helicity effect may work in this type. So as you know, helicity gives the turbulent structural information. Like this. Then, so in addition to K and epsilon, this K is the intensity of turbulence, intensity of nature, and epsilon is how energy is cascading to small scales. In addition to these, how to say, intensity of nature quantities, I add this quantity. Then this is the same expression I already showed. And then okay. So without any helicity effect, initially dented flow profile very rapidly recover to flat profile. But with the helicity effect, such dent tendency recovered. So anyway, so primary effect of turbulence is enhancement of effective transport, but in the presence of symmetric breakage, enhanced transport may be balanced by some other turbulence effects. So in addition to intensity information of turbulence, structure information is important, and helicity can be. And this is several explanation of why this is a very good, famous, celebrated experiment by Kito, and I also consider some variational analysis using helicity. So in addition to entropy, we consider helicity. This is something like John Bryan Taylor's Taylor state argument, very similar to. Then if we have no constraint, we only have a flat profile, but we have a constraint of helicity, then we have this type of equation. Then we can estimate flow reversal condition using the solution of this one. Then we can write a diagram of helicity and flux, actual flux of flow. Then if compared to flux, if we have a very strong helicity, we have a reversal of flow. Then this is a comparison between my formalism and it shows. This is all these things shows the reversal, and these are not reversal tests. Anyway, so now I finally I entered the vortex dynamo.
How much do you need to finish?
1/3 I reached.
Okay, I have to leave in a little bit less than 15 minutes from now.
Okay, so I will run. Okay. So if we already know the Reynolds stress expression. So we have turbulent electromotive force or quantum motive force expression using this relationship. Then we have electromotive, vortex motive, quantum motive force of this. And as I already showed, Reynolds stress depends on the gradient of helicity. So quantum motive or vortex motive force depend on the one more derivative of such quantity. So this gamma is gradient H and D is divergence gamma. So this is Laplacian H of something. So I will skip. Anyway, we have in the early stage of there are terms, helicity inhomogeneity related terms. So if we have no inhomogeneity of helicity, this term disappears. So in this work, inhomogeneity of helicity is very essential. So anyway, so I will consider, okay. So this type of, because I don't make any numerical simulation, so I make some assumptions. Then in the case of large horizontal scale, then only gradient is Z component. This is radial component. Then we have a contribution to the induction rate. Induction rate is a Carl vortex motive force, something like that. At the early stage of induction, if we only retain this rotation term, then we have this contribution. So which gives omega f cross gradient d gamma. So d gamma is Laplacian of helicity. Okay. Anyway, so in such a case, if we anyway, so this is if we have a rotation omega f, then we have a vortex induction in x direction. This is azimuthal direction.
So no helicity at the moment, yeah?
Helicity is here.
Ah, sorry.
D is helicity, Laplacian helicity.
You would like to get a steady-state solution of equation for vorticity or what? Because when you speak about vorticity dynamo, you need to solve dynamical equation in order to determine growth rate and conditions for vorticity dynamo.
Yeah, I should have calculated at least growth rate or something. Yeah. If it is possible. You know? so anyway, I will try during my stay here. Anyway, so my point is, coupled with rotation, coupled with inhomogeneity of helicity, the large-scale vortex may be induced in perpendicular direction to omega and also this quantity. So in this case, we have a x direction. So I think this may related to this type of Saturn's white spot observed by Hubble Space Telescope. You see
White spot or red spot?
white spot, Saturn's white spot. No. So you see this type of. I think this is a helical structure, but someone may agree, but I don't know. Anyway, so this is, and once X component of omega induced, so another component can be follows. And other opposite situation is this type of small horizontal scales. I think this is related to generation mechanism of tornado, part of generation mechanism of tornado or something. So in such a case, we have a Z component, so vertical component of induction. So, but still we need some numerical or some quantitative estimate.
So this IV is a source term in the mean.
This is IV is Carl VM. VM is vortex motive force. So this is coming from totally coming from turbulence.
So it's a source term in the Rotizzi equation, or even the large scale Rotizzi equation.
No source term. You mean rotation, system rotation.
I mean, I thought you were talking about the vorticity equation.
Vorticity
Or the
equation.
mean vorticity even. No? Yeah. And then that's
This one?
there.
So no external source term.
Yeah, because it itself depends on V, I mean.
Yeah.
So last term is determined by turbulence,
Yeah, this term is coming from turbulence.
But this equation is not closed, because you have equation for mean vorticity, which depends on helicity. Helicity is a given. And then you need to
Helicity is given.
have
What do you mean by helicity is given?
Sorry?
What do you mean by helicity
Helicity
is
is
given?
given by background turbulence. So you need additional equation for helicity, dynamical equation. Because you said that
Helicity is not given.
it's
Not given. At least the quantity of helicity is not given. I only assume in wave number space some spectra of helicity.
No, this I understand.
Not. Helicity can be zero also. If we have helicity itself will evolve in
but
the framework of this equation.
Yes, in the mean field equation, you have second derivative of kinetic velocity.
In mean field, mean velocity.
In equation for the mean vorticity, you have second derivative of kinetic velocity.
Yes, and also kinetic helicity should be solved by
So,
itself.
yes, so you have a coupled system of equation. One for kinetic velocity and one for mean vorticity.
Yes, and also mean energy.
And
Energy.
so
Yes,
three equations. So you
and
need to solve three
dispersion
equations.
rate.
Yeah.
If we try to fully solve. But
Yeah, of course.
using some, for example, pencil code or something, we can add, impose some profile of helicity as a condition, or
As an
we can
initial
impose.
condition.
Pardon?
As initial condition,
Not necessarily initial.
but your generation mechanism depends strongly on the second derivative of kinetic velocity. So if
Yeah.
you choose some profile, of course, you can find some profile in
Yeah,
generation, but
that's
it's
the
not
first
problem.
step. That's the first step. Of course I know, so helicity itself should be solved. Of course, I understand. I agree with you in this. But first starting point is assume some profile. This type of D or gradient D has finite value. Then see how it works or not.
Yeah, okay, sure.
And final topic is subgrid scale modeling. So as you know, large eddy simulation is large scales of motion is simulated with modeling of small scale. Okay, so representative model is Smagorinsky model. In Smagorinsky model, we have filter width and also shear, magnitude of shear. Then viscosity and everything is modeled using delta and S. My proposal is to express the property of this part. Helicity should be included. Deserved to consider. So Smagorinsky model is this one. And as you see, if we consider the equation for subgrid scale energy, okay? Subgrid scale energy is written like this. This is exact. Then, if we assume the production is balanced by dissipation, this argument is very similar to quenching argument of alpha, beta, and gamma, everything. So, if we assume some balancing of production and dissipation, then we have this result. Then this production term is expressed using S and delta, and also dissipation rate is using nu and S. Then we recover the Smagorinsky model. So Smagorinsky model is a consequence of the balancing between the balance of production and dissipation. So local equilibrium is very important. So if such local equilibrium breaks, Smagorinsky model is easy to break. Anyway, so this is the essence of Smagorinsky model. So this is very similar to mixing length argument and also quenching argument. Anyway. So drawbacks of Smagorinsky model is several, and lack of self-adaptivity. So subgrid scale viscosity should vanish in the region when the flow is fully resolved, and also decay corrected in the near wall region. So we need some wall damping function, and also we have